स्टार्ट कर दो
फुल नहीं खुल रही है सर, फुल मोड कैसे है सर इसमें? फुल मोड खोल लो, कंट्रोल
F5 से नहीं आएगा।
Good morning.
बैठे हो ठीक है।
In this session, Dr. Sunjit Chinde is going to talk about structural, electronic, optical, and mechanical properties of crystalline and heterogeneous nanotube of group 4 elements. And he's HOD of the department, and he published around 10 research papers in various journals. So I request Professor Sunjit, please continue.
Worthy coordinator of the program, Dr. Arunji, and dear participants, today's lecture is just an overview of the properties which can be studied by the help of sister code. So the topic which I am going to elaborate is structural, electronic, optical, as well as mechanical properties of pristine and heteronanotubes of group 4 elements, that is by namely carbon, silicon, as well as germanium. First is theoretical formulation, then we have studied here pristine and histone nanotubes of group 4 elements. The pristine nanotubes are what? These are the nanotubes having same kind of atoms, whereas heteronanotubes consist of different kinds of atoms. Then next is encapsulated as well as functionalized silicon nanotubes. Encapsulation we are doing in the sense that we are putting some sort of atoms inside the nanotubes, then we are studying its properties. Then functionalization is that we are putting some kind of wire or atoms on the surface of a nanotube, and then again we are studying the properties. Then it is again intercalation of alkali metals or atoms, alkali atoms or ions into pristine as well as heteronanotubes. So we have taken for this intercalation lithium, sodium, potassium, also because sodium and potassium also belong to the same group. So with this possibility that besides lithium, sodium and potassium can also be a source for the power storage batteries. Dear participants, dates back we also started our work with myself and Arun, Dr. Arun started our work with liquids, but the Sesta code was not quite compatible with Sesta code with liquids. It was not quite compatible with liquids because it involves large number of atoms and then large number of computational cost. So Dr. Aluwalia suggested me to switch over to another system, and that was just silicene. Silicene here, just you have heard about graphene, तो उसी का ही काउंटर पार्ट उसी ग्रुप में ये हमारा सिलिसियन बनता है. So we started with nanotubes of carbon, silicon and germanium of that group, of carbon group. So nano structural materials have been the hottest topic of research. And then what is different here? Here different is from the bulk, from their bulk counterpart, what we have different. Number one, distinct density of states. Then increased surface to volume ratio. Then confinement of electrons. We know electrons are confined in one direction or two directions in nanomaterials. Then surface to volume ratio is also very large in nanostructure materials, as we know. Suppose this is our graphene sheet, then monolayer atoms are there, then volume is negligible, then surface to volume ratio is very high. This is another reason for very different properties of the material at the nanoscale. Then confinement of electrons is also there. We are confining the electrons only in one direction or two directions. Then distinct density of states, because otherwise we just observe bands. So instead of bands, we are getting splitted lines over here. Then classification of nanomaterials. Nanomaterials can be of two dimensions, just as nanofilms. Here we are, what we have is one dimension is less than 100 nanometer, whereas in case of one dimensional nanomaterial, our two dimensions are less than 100 nanometer. And in case of nanoparticle, we are confining all the three directions. That is, all the three directions are less than 100 nanometer. One-dimensional nanostructures due to confinement in the two directions can be regarded as the most promising building block for nanoelectronics. These can be nanowires, side by side biaxial nanowires. These can be nanobelts, nanotubes, as well as coaxial cables. Now, again, coming to the nanotubes, what we have is, suppose I am putting some hexagon-like structures over here, then I will get a honeycomb structure. These are hexagon here, and you suppose that all the hexagons are repeated over there in this sheet. Then it is monoatomic thin layer, that is the surface. Then suppose it is graphene. In case of silicon, it is silicene, and in case of germanium, it is germane. Now, what the interesting thing about these nanotubes is, I can make a fold of this paper in different ways. Okay, I can fold it like this. I can fold it like this, then again I can fold it like this. Geometry is getting different, and then I can one more fold I can give like this. So geometry is again a different. So the interesting thing about this is, once we get armchair-like geometry, means two arms-like structure, then it is zigzag structure also. Then in addition to that, we can also have chiral structure. Chiral means other than zigzag. So on rolling the sheet, we can have three types of nanotubes. So this was single walls nanotubes. Then if I want to construct the multi-wide nanotubes, then suppose my upper sheet is smaller, then lower is a bit smaller, then larger one is more smaller, then I am again rolling is like this, then these are multi-wall nanotubes.